And to start with is if we just have so-called scalar data, so data that only mean one, only are related to one variable, for instance, observations of groundwater depth at many at different times, for instance, or we just collected samples of groundwater salinity at many locations without recording the location itself. We just have these bag of samples. Then we are dealing with so-called univariate statistics. It can also happen that you measure at one location, you measure two different variables that are related. For instance, porosity and hydrological conductivity from one sample, and you have many of those samples, or you measure groundwater depth and groundwater salinity at one location, and then at many locations. So these are so-called bivariate statistics. So they relate to two different variables that may be related statistically to some extent. And then finally, there's multivariate statistics. That is if you have three or more properties that are recorded for every sample. For instance, you get multivariate statistics if you have, this is an image that you're going to see a lot more in this course. These are 140 locations where one has observed a certain variable, for instance, concentration of lead content in the soil, for instance. And what you have here is for every sample you have three variables, an x coordinate, a y coordinate, plus some property. In this case, lead content, for instance. Yeah. So those are, to deal with that, to describe these type of data, one uses so-called multivariate statistics. The description of multivariate statistics will be treated in only not before chapter 5 and chapter 6. Or 7, sorry, on random, so-called random functions and geostatistics. Here we will limit ourselves to univariate and bivariate statistics. So starting with univariate statistics, the simplest way to describe data where you have scalar data, so you just record one variable, is by looking at making a so-called histogram, yeah, or frequency distribution. So what you have is you divide the whole scale in over which you have data. The individual data values are here are the red little stripes here, yeah. And then you count the number of data in each interval. Such an interval is called a bin, and an interval is divided in by breaks. So this is the break between interval. This is a break. This is a break. Let me get the pointer out. Sorry. So this is a break, and this is a break, and in between is the bin. So you just count the number of those. That's called the frequency distribution, and then we can actually get the count the number of data that are in between those locations. That's in this case 22, and that's the value that is plotted. So for instance, between 20 and 25, there's 22, and that's the value that is plotted. By the way, the bin with the highest value is often called the center of that. That's called the modus of the distribution. Yeah. Now, often one wants to normalizes the number of counts per bin. You normalize it by dividing by the total number of data in the data set, and then you get a relative frequency distribution or a density. Yeah. So this is either called the relative frequency or the density. Another way of so if we look at this, we can actually already get something that resembles a probability. For instance, if we want to know what is the probability that a value z, suppose z are observations of groundwater levels in a field, and you want to get an idea of what the probability is that the groundwater level is between 20 and 30 meters. Then you can actually derive that from by adding up the relative frequencies of these bins, so that the area underneath this bin. So that is that is the relative frequency 0.044 multiplied times 5 plus the area underneath this one, that is 0.028 times 5. So we get a probability of 0.36. Yeah. Of course, you know this. From this, we also see if we add up the areas of each of those bins, we end up with something that's equal to 1. Right? So that is how you can already get a probability, at least within the range of your data, from your relative frequency distribution or density function. Now, another way of presenting your data is not using a histogram, but using a cumulative frequency distribution. How is that done? Well, you start with the same amount of data. You order them in ascending order from the smallest to the largest, and the order is transferred into a distribution value by taking the order and divided by the number of data plus 1. Yeah. So from this, we can easily already set, well, the probability that z is smaller or equal than 30 can be read from this curve, which is 0.85 in this case. Yeah. So that's the cumulative frequency distribution. Now we can also get the probability frequency distribution to calculate the probability that the value is in between 20 and 30 by taking the probability that it's smaller than and equal to 30 and then subtracting the probability that it's smaller or equal than 20. Yeah, so we get this value minus that value, and we arrive at the same 0.36 as we also calculated from the density or the histogram or the density function. So that is so basically they are actually two sides of the same coin, as you can see. Yeah. So we can get this probability that z is in between a certain value directly by reading it from the cumulative frequency distribution, or get it from the relative or the histogram or relative frequency or density distribution. Yeah. Okay. Now, what one often does is try to describe somehow the form of these histograms. So, what is the form of the histogram? How would you define it? And for this, we use different type of moments. So, of course, the obvious one is the center of mass of the data, which is the average of all the data in your data set, and this is called the mean, which is a measure of locality. So, what's the center of mass of my data set? Yeah, that's the mean. Another one, apart from the measure of locality, is a measure of spread. So how wide is this distribution? Is it just small or is it wide? And that is called the variance. And the variance is calculated by taking each data value, subtracting the mean that we previously calculated, square it, and then adding it all up, and then divided it by the number of data. Yeah. Actually, an alternative way of computing it is taking the average of the data value squared and then subtracting the mean squared. Yeah. Now, the larger the variance, the wider the distribution is. So this is a small variance. This is a large variance. They may have the same mean, but you can see this has a small variance and this is a large variance. Yeah. Now, likewise, we can also take, you've known this one, that's the square root of the variance is the standard deviation. And there's also a thing called the coefficient of variation that says something about the relative width of the distribution compared to the value of its mean. So we take the standard deviation and divide by the mean. Now the coefficient of variation only has meaning if we're dealing with strictly positive variables. So groundwater level would not be a good one because depending on the reference level you take, it can actually be both positive and negative. But for instance, hydraulic conductivity or concentration are strictly positive variables, so they can be 0 or larger than 0 only. And these one-sided distribution, we can actually use the coefficient of variation. Now this is often also called the second central moment. There's also the third central moment that is called the skewness of the distribution. It tells you whether a distribution is negatively or positively skewed or is neutral, it's symmetric. Yeah. So this is the skewness coefficient, and the skewness coefficient is calculated by taking the value, subtracting the mean, raising it to the power of 3, and then taking its average value of the sum. Yeah, so taking the sum of that and then divide by the number of data you have, and then you normalize it by the standard deviation to the power of 3. If this thing is 0, it is more or less symmetrical. If it's negatively skewed, then it has a thicker tail on the right, and here it has a thicker tail on the left. A fourth moment type of thing is called the kurtosis. That is basically the peakedness. So if it's how peaked it is, so how much of the probability mass is in the center compared to on the side. And if it's flatter than that, it is positive. If it's more peaked than average, it's negative. And that's compared to the peakedness of the Gaussian or normal distribution. We will come to that distribution later on. How is it calculated? You take the value of the data, you subtract the mean, raise it to the power of 4, take the average of that, and then normalize by the standard deviation to the power of 4. And for a normal or Gaussian distribution, this thing would be 3, so we subtract 3 to have something to show whether it's more peaked than the Gaussian distribution or less or flatter on the top than a Gaussian distribution. So these are four different measures that describe the form of the histogram or the cumulative distribution of data. So the mean, the variance, the skewness coefficient, and the kurtosis. Now a more complete way of describing a data set is by looking at the so-called quantile or percentiles. For instance, the 90% quantile is that value where we have that 90% of the data are smaller than that value. Yeah. So this is and how do you find it? You take 0.9 here on this axis, you go like this, and then you find a value on the variable axis here, and that variable is called the 90% quantile or 90 percentile. Now a special type of quantile is the median, because that is the 50% quantile. 50% of the data of the median are larger and 50% are smaller, as you can see. And then there's also so-called quartiles. So the 25% quantile is the first quartile, the median is the second quartile, and the 75% quantile is the third quartile. And the range between the first and the third quartile is called the interquartile range. And this is an alternative way to describe the width of the distribution. So we can talk about the width of the distribution in terms of the standard deviation or the variance, but often one uses also the interquartile range. And the reason is because the variance or the standard deviation is only a reasonable measure of the width of the distribution if it's a little bit more or less, well, if the skewness coefficient is close to 0. So if you have a more or less symmetric distribution, then the standard deviation is a good measure of spread. But if you have a very skewed distribution, for instance with a very long tail, which you for instance have with hydraulic conductivity, many small values and a couple of very large ones, then the interquartile range is a better and robust measure of spread. Now we can summarize all these different statistics in one little plot, which is called a box and whisker plot. It's called a box and whisker plot because this is a box, and these are whiskers, like the whiskers of a cat, right? And the box is the difference between the, so this is the values, on this axis you plot the values, yeah? And here you say, okay, this is the first 25 percentile or quantile, this is the 75% quantile, so this is the interquartile range. You plot the median here as a stripe and then the mean as a cross. And you can see that the mean doesn't have to be the same as the median if it's skewed on this side. The length of the whisker is either the minimum or maximum value, but it cannot be longer than 1.5 times the interquartile range. So this value here can never be farther away from the third quartile than 1.5 times this distance. Yeah? So if a maximum value in this case is outside that range, it is often seen as an outlier. So it is often used for outlier detection. For instance, here we see a box plot that was made in R. Here you can see this is equal to the minimum value, but here it is actually 1.5 times the interquartile range removed from the third quartile. And you can see that 3 values fall outside this range. So they are extremely outliers compared to the rest of the distribution. Now, it doesn't mean that we have to get rid of these data in a subsequent statistical analysis, but we have to take a closer look. Are these outliers real, or are they and we really have such a skewed distribution, or are they maybe mismatches? Are they maybe data that are taken from another location, or there's large errors in the observation and so on? It just says if you do an outlier detection with a box plot, just tells you where to inspect certain data values with more care. Now finally, these are so-called box and whisker plots, as you can see. This is from my own PhD research a long time ago, where they're also very handy to look at different categories and data sets to compare them. For instance, this is the logarithm of the hydraulic conductivity measured at many samples, and these samples are in different categories depending on the type of texture that was identified for the samples. And you can see, for instance, right away that, for instance, if we compare the hydraulic conductivity of fluvial sands with that of aeolian sands, that they have the same mean value, but the variation is much larger in fluvial sands than in aeolian sands, which are much more homogeneous. So it's very interesting to compare the different distributions like this. Now, of course, box plots are one way of comparing distributions. There are many other ways, and one that's particularly popular these days are these so-called violin plots, and you can find them also in all these different type of softwares can actually make these plots. Now, if you want to get an overview of the descriptive statistics, you can actually go to this little thing called rdescriptive.r. It's also on Blackboard, and you can play around with it. You load it into R, and you start playing with it. Yeah. Okay, let's move on to bivariate statistics. Now, if we have two variables, for instance, porosity and hydraulic conductivity, and we want to see whether they are related, we can compute the so-called covariance. The covariance between any two variables is taking, for instance, for all the Z data, you compute the mean. For all the Y data, you compute the mean. So this is hydraulic conductivity. We compute the mean hydraulic conductivity. We subtract the mean from each data value. We do the same for porosity, for instance, here. Y minus the mean of Y. We multiply those deviations with each other, and then we add them all up, and we divide by the number of data that we have. Again, this is another way of doing that, taking this cross product and then subtracting the product of the means. This is the so-called covariance. And the covariance, if the covariance is 0, then the two are not related. If the covariance is larger than 0, then a larger value of Z will go together with a larger value of Y, which is expected, for instance, for hydraulic conductivity. But it can also be negative. So, for instance, you can imagine that a larger value of recharge goes together with a lower value of salinity, for instance, right? I mean, so they can also have a negative association, and then the covariance becomes smaller than 0. Now, often we like to normalize the covariance, so we compute the covariance and we divide it by the product of the standard deviations. So this is done here. And then we get the cross-correlation coefficient, which is, as you can see here, and the cross-correlation coefficient varies between -1 and +1. So we saw this, the correlation coefficient, and this is the little tool that we played around with. And this shows you how the correlation coefficient goes. It goes from +1 to 0 to -1. Now, of course, if it's 1 or -1, it doesn't say anything about the slope, because that depends on the range of Y and Z. It only says that they are on a straight line. What is also important to notice is that all of these patterns that we show here have a correlation coefficient of 0. But you can't say that there is independence between Y and Z. There's only no linear dependence. So there's definitely a structure here. There's definitely dependence between Y and Z, but it's just not linear. So you can say that if something is statistically independent, the correlation coefficient is 0, but you cannot say the other way around. If it's 0, it is statistically independent. It is only linearly independent, but it can still be dependent on a higher order. For instance, in this case, it is a parabol. Here it's a circle that can be described. So that is very important to understand.